Thanks for joining us in the review of aerodynamics of race cars. This review is really aimed at technicians, mechanics and engineers that really want to learn more about aerodynamics, and specifically, what CFD is about. In the study of aerodynamics, there's really only two main unknowns, and that's pressure and velocity. Pressure is a force acting over an area. It acts normal or perpendicular to a surface. It has only one direction, and that's normal to a surface. Velocity is the directional speed of the air as it flows across the body. It has three directions: velocity in the x direction, y direction and z direction. These are the Navier-Stokes equations that were developed in the 1800s. They are the basis for all types of fluid motion. These include gases and liquids. In our case, air moving across a body. These are partial differential equations shown in vector form. The great thing about differential equations is you get a clear understanding of physically what's going on. Nothing could be further from the truth. They say that mathematics is the language of physics. I would say that it's a foreign language. It's like trying to understand electric or hydraulic schematics without knowing what the symbols stand for. Keep in mind that this is about understanding the basis of aerodynamics, to reduce your times by a few tenths or a few seconds, based on your type of racing. It's not necessarily about understanding the divergence of flux fields. If we zoom into the continuity equation, which is sometimes called conservation of mass, at first we see an upside-down triangle. This is the del operator. It operates on the velocity vector v. It is the partial derivative with respect to x, y and z. The partial derivative symbol is the letter d with a squiggle on the top. It represents small changes. Hang with me for a bit. The bold v represents a vector of velocities, u, v and w. U being velocity in the x direction, v is velocity in the y direction and w is velocity in the z direction. These directional vectors add up to the main vector v. This dot product operation results in the following form. Don't let this scare you, and keep in mind that most engineers never use calculus after leaving college. To better understand what this means, we need to look at a typical mesh. If we zoom into one cell, we can call this a control volume. The conservation of mass equation is saying that the mass flowing into a cell must equal the mass flowing out of the cell. The partial differential equation shows that it has three directions, x, y and z. Math heads refer to this as divergence. It's assumed that the air density, shown in red, is part of the equation which results in mass. So what this equation is saying is that the mass flow into a cell must equal the mass flow out. Sometimes a simple concept to understand results in a difficult mathematical operation. So, if we now zoom into the Navier-Stokes momentum equation, we see this as another differential equation in vector form. As before, this vector form makes it difficult to understand. The bold U means the vector form of the velocities in the x, y and z directions. If we uncondense this vector form as before, we end up with three differential equations. It looks complicated, but if we look at the x momentum equation, we assume that most aerodynamic studies are at a constant speed, say 150 miles per hour. This means the first local or transient term can be ignored. Gravity can also be ignored. So now we're looking at the reduced form, x momentum equation. If we rearrange things so the forces are on the left side, there is a pressure force and viscous forces. Viscous forces are the resistance to flow. Certainly if the fluid was water, as compared to air, the viscous forces would be much greater. Therefore in aerodynamics, pressure forces are much higher than viscous forces. On the right side the first factor is ρ, the density of air. It is the mass, per unit volume. The factor enclosed by the parentheses represents the fluid acceleration. This format is known as Newton's second law. Force equals mass times acceleration. It's a universal law of dynamics, applied to fluids. So now we apply this format to the y and z directions, we get the three momentum equations arranged in Newton's second law of motion. we can add the previously formulated continuity equation. This results in 4 equations to constrain the solution process. Recall that our unknowns are pressure and velocity. Things like downforce and drag are calculated from these unknowns. So, we end up with 4 unknowns. Pressure, which is normal to the cell surface, and 3 velocities to cover the x, y, and z directions. 4 unknowns need 4 equations for a solution. These are the 4 equations. While these are the basis for the Navier-Stokes equations, there are a few other important quantities calculated during an aerodynamic analysis. That is, turbulence, vorticity and shear stress at the surface level. These might be covered in a future video. So, we started out with the 2 Navier-Stokes equations in vector form. We expanded those equations into partial derivative form, and tried to make sense of what their meaning was, at a high level. We tried to clarify that these equations were applied at the mesh cell level referred to as a control volume. So, when somebody mentions Navier-Stokes, you should have a basic understanding of what these equations mean, and know that these are the basis for computational fluid dynamics, often referred to as CFD. We plan on working part 2, which could cover the solution process, or understanding CFD outputs, and the various color plots, but we are open to any direction, based on your comments below. These are some references for deeper learning. You deserve a free t-shirt if you made it this far. The first 25 people that email me your size will get a free t-shirt. We appreciate that you watched this video, and have a great day.